Welcome back. We've been doing a lot of work on limits, and you now know that the notation and limit problem you see here asks, what value does the function approach as x approaches -2? That's not always an easy question to answer, but today we'll learn some limit laws, tools that make finding some limits easier. Let's get started. So far, we've been using graphs and tables to estimate limits. While those can be helpful for visualizing how a function behaves, it's not always the most efficient approach. Here's the good news. There are some universal special limits and limit laws that allow us to evaluate limits without graphing. Let's start by taking a look at 4 special limits. These limits apply to very basic functions and will serve as building blocks for more complex cases. The first special limit refers to the limit of any constant function c. As x approaches any value a, the limit of c is just c itself. The second special limit is the limit of the function x. The limit of x as x approaches a number a is simply that number a. The third is the limit of the general power function x to the n. The limit of x to the n power as x approaches a is a to the n power. And the fourth is the limit of the nth root of x. The limit of the nth root of x as x approaches a is the nth root of a. Let's give these a try. In your guided notes, use the special limits to find each of these 4 limits. Now we'll look at them together. Which special limit helped you on number 1? Right! This is a power function. Since x is being raised to the 3rd power and x is approaching 2, I know that the limit will be 2 to the 3rd power, or 8. What about number 2? We're taking the cube root of x, and the limit as x approaches 2 is the cube root of 2. On number 3, which special limit did you use? We're finding the limit of the constant, 5, so we need the first special limit, which tells us that the limit of 5 as x approaches 2 is just 5. Finally, number 4, we need the limit of x as x approaches 2. The limit is equal to 2. If you got all of these right, great work! If not, take a minute to review these special limits before moving on. We have these 4 special limits, but what happens when we face more complex functions like number 5? From the special limits, we already know how to handle x raised to a power, a simple linear x, and a constant. But the special limits don't tell us how to handle multiple terms combined together or when a term is multiplied by a constant. That means we need some limit laws for more complicated functions. Let's check them out. Here are the first 3. The first 2, the sum and difference laws, are closely related. The sum law says that the limit of a sum is the same as the sum of the limits, as long as x approaches the same value a. And the difference law says that the limit of a difference is equal to the difference of the limits. These first 2 laws tell us that we can break limits apart across addition or subtraction. The constant multiple law tells us that when an expression is multiplied by a constant, we can first find the limit of the expression, then multiply that result by the constant. Let's put all of that together and find the limit of the function in number 5. The sum and difference laws say that we can break this function into parts, find the limit of each term, and then add or subtract the results. Let's start with the first term. The constant multiple law says that we can pull out the coefficient 2 and multiply it by the limit of x cubed as x approaches -1. Next, we can subtract the limit of the second term. Then we'll add the limit of the constant. Now that we've broken up the terms of the function, we have 3 limits that we know how to evaluate. Use the special limits and finish finding this limit on your own. Let's see how that went. The first term is a power function. The limit of x cubed as x approaches -1 is -1. The second term is just a single linear x. The limit of x as x approaches -1 is -1. The third term is a constant. The limit of 5 as x approaches -1 is 5. Finish by simplifying to find that the overall limit is 4. Now let's find the limit in number 6. Some of these operations should look familiar. They're covered by the first 3 limit laws, which are listed in your guided notes. But this function includes a product and a quotient. We have 2 more limit laws to help us here, one for products and one for quotients. Law 4, the product law, tells us that the limit of a product is the product of the limits. Law 5, the quotient law, says that the limit of a quotient is the quotient of the limits, but only if the limit of the denominator isn't 0. Let's start by rewriting the function using these 2 limit laws. We can rewrite the numerator as the product of the limits, and we can divide that numerator by the limit of the denominator. Each of the 3 limits we have now are similar to ones you've already seen. Use your guided notes, the special limits, and the limit laws we've discussed so far to finish evaluating the limit for number 6. One tip before you get started, it's always a good idea to check your denominator first to be sure it's not equal to 0. Once you have a final answer, come on back and we'll go over it together. How did it go? I started by separating these limits out even further. And now we can go through each one step by step. First, we have the limit of x squared as x approaches 2. I know that I can substitute 2 for x, and the first factor in the numerator will be 4. The second factor is 3 times a linear x. The limit of x as x approaches 2 is 2. After that, we're subtracting the limit of a constant. The limit of a constant is that constant, so we'll subtract 4. We'll simplify all of that in a moment, but let's turn our attention to the denominator. I used some mental math to be sure it wouldn't be equal to 0. Now we can multiply 5 by the limit of x cubed as x approaches 2. Substituting 2 for x tells us that the limit is 8. We can clean all of this up a bit and get ready to simplify. I get 8 over 40, which reduces to 1/5, and that's our limit. We've reached our last example for this video. We have another rational function, and the quotient law says that the limit of a quotient is the same as the quotient of the limits. But now we need some limit laws that will help us deal with the radical in the numerator and the exponent in the denominator. Here are the final 2 limit laws. Law 6 is sometimes called the power law. It says that the limit of a power is the power of the limit. The power law for general limits extends what we saw in the special limits. Instead of just x to the n, it applies to any function raised to a power. Law 7, the root law, says that the limit of the nth root of a function is the nth root of the limit. I encourage you to pause your video and finish number 7 on your own. Then come back and we'll go over it together. Let's see how that went. Again, I started by breaking the function down and separating out each limit term by term. In the numerator, I'll take the cubed root of the limit of x to the sixth as x approaches -2. So first, I find the limit of x to the sixth by substituting -2 for x. That gives me -2 to the sixth, which is 64. Now, let's look at the limits in the denominator. Here, I can find each limit separately and then raise the entire result to the third power. First, I'll take the limit of x as x approaches -2. That's just -2. Next, I take the limit of 3, and since it's a constant, the limit is simply 3. Now, I can simplify everything to get -4 125ths. Here are the special limits and the general limit laws we have looked at today. Remember, these are in your guided notes, and you can refer back to them anytime you need to. Let's wrap up this lesson with a bit of practice. Use your guided notes and find each of these 4 limits. I'll show you my process and answer for each one briefly, along with a few reminders of things to look for. Feel free to pause your video at any time if necessary. Here's my work for part A. The limit is 46. Remember, the special limits tell us to substitute -3 for x in both of these first 2 terms. But for the third term, remember that the limit of a constant is that constant. Here's part B. The limit is 48. To find this one, I separated out the product into a products of limits, and then found each individual limit. The limit on part C was -1/7. To find this one, I separated out the quotient into a quotient of limits, and then found each individual limit using the special limits. And finally, here's part D. The limit is 1/3. To find this one, I again found the quotient of the limits, and I also needed to use the root law to find the square root of the limit. Today we learned that evaluating limits doesn't always require graphing or creating tables. Instead, we can use the special limits and limit laws to break down complex functions into simpler parts, making it easier to find limits algebraically. Remember, use the special limits for constants, powers of x, and roots. Apply the limit laws to handle sums, differences, products, quotients, and powers. And always check for undefined terms, especially in quotients, before evaluating the limit. These tools will help prepare you for more advanced problems. Check to be sure your guided notes are complete before moving to the lesson activities and online practice. And remember, the next lesson includes a wrap-up assessment, so be sure you've completed each lesson in this section before moving on to that wrap-up. See you next time!
Hey!